So this is continuing chapter 16, talking about salts. And probably the trickiest part of this whole calculation portion is identifying that it is a salt and making sure that you know how to do these types of calculations. So if I want to find the pH of a 0.1 molar sodium acetate solution, I'm giving you the Kb value. So I'm kind of giving you a hint that you're probably going to make a basic solution, but please recognize that sometimes I might not give you the proper K. So take a look at the sodium acetate and go, okay, I'm going to put this in water. So sometimes I'm going to write water above the arrow, sometimes I'm going to write it next to it. So I have the sodium ion and the acetate ion. And then you want to look at the two ions and say, okay, who is going to react with the water? Well, the sodium is coming from a strong base, so it's not going to go backwards. It can't go backwards to produce sodium hydroxide. So it's not going to be involved, but the acetate is going to do something. So I could take the acetate ion plus the water at equilibrium. It will make acetic acid and hydroxide. Okay. Now, we do know that if I start with a 0.1 molar on my container, that's going to give me 0.1 molar of my acetate ion. So this is 0.1 molar, and I have none of these two to start with. So this goes down by X, this goes up by X, this goes up by X. And again, you don't need to show this, but I'm just showing it for the notes so that if you look back at this, you can kind of reference where we got all of these numbers. So I am looking at a Kb. So I'm looking at the acetic acid times the hydroxide ion concentration over the acetate ion. So these look a little different in terms of on the bottom is not going to be the base. It's going to be, again, the ion that reacts with the water. So what's on top is the X squared. What's on the bottom? 0.1 minus X, and this is equal to your Kb, which is 5.6 times 10 to the negative 10. Again, same rules apply. This is 10 to the negative 10th. So that must mean that this is pretty small in amount of dissociation. So I could cross out that X and I'm probably going to be perfectly fine. So when I solve for X, I get about 7.5 times 10 to the negative 6. Again, look at that number. That's a pretty small number. That's my concentration. Well, what's the concentration of? Well, it's the concentration of the hydroxide ion concentration. Again, it's also the concentration of acetic acid, but that's not H plus by itself. So you're not using that for your pH. So this is your hydroxide concentration. So if I take the negative log of it, I'm going to get my pH of 5.12, 2 sig figs after the decimal. Again, your brain should be going, this can't be my pH because I'm producing OH. So this is too low of a pH for a basic solution. So I subtract that from 14 and my pH comes out to be about 8.88. And again, rounding issues aside, okay? So again, the trickiest part with these kinds of calculations is recognizing what is taking place. So again, I think you could write out all of this and see what you got, okay? So why don't you try the next one in your note packet, find the pH of a 0.2 molar sodium sulfate solution. So why don't you try it? I'm going to come back and show you the answer. So sodium sulfate breaks up into sodium ions and sulfates. So sodium, again, is not a player here. SO4 is going to be what you look at. So SO4 has to take on an H when it's reacting with water to make HSO4 minus and OH minus. So since it's taking on an H, this is acting like a base, okay? So you look up the Kb value for SO4 2 minus. That's what you're looking up. And when you look it up, it's about 8.3 times 10 to the negative 13. That is equal to X squared over the initial concentration, which is 0.2 minus X. So we're going to cancel out the X on the bottom. You solve for X and it comes out to be 4.1 times 10 to the negative 7th, and that is your concentration of hydroxide. So again, if you take the negative log of your number and you don't think about it, you're looking at 6.39. Your brain should tell you I'm producing OH, I have to have something greater than 7. So obviously my pH is 7.61. Now recognize the last one we did was 10 to the negative 10th. This is 10 to the negative 13. So you will see that the pH is going to fluctuate very much by that Kb or Ka value, whatever it happens to be, also dictated by concentration. But always please be sure that you are looking up, again, using this table, that you can look for, you know, what ion you're talking about. So this is your Kb value, so it's in the Kb column when you're looking at it. All right, so the last one I'm going to do with you, because it's a little more tricky, because it is sodium hydrogen sulfate. It is a 0.2 molar. So again, I just like to write this out in the notes. You don't necessarily have to do this step, but it's more for you to understand that this salt completely dissociates. So keep in mind this arrow is only pointing in one direction when we're talking about salts. So the Na doesn't get involved, so it is the HSO4 minus reacting with the water. Well, this one's a little more tricky, because am I releasing an H, or am I going to take on an H? Can I go backwards and make H2SO4? Is that an okay thing to do? No, because this is a strong component of that acetic acid. So that's really why I went through that example of acetic acid. Excuse me, why do I keep saying acetic acid? Sulfuric acid. Why I keep going over sulfuric acid is because it is so unusual. And when you run into it as a salt, you need to understand that it doesn't go back this way. It can't, because this is a strong, so it doesn't go this direction. So that means the only thing you could do is make the sulfate ion, and you end up with hydronium ion, okay? So this is looking at a Ka, okay? So you have to go and find HSO4 as a Ka, okay? So go up to the top here, okay? HSO4 minus hydrogen sulfate ion is 1.2 times negative second. So that is my Ka for this salt, this ion. It's going to be x squared over 0.2 minus x. Same thing. Cross out that x. The x that you solve for here comes out to be about 4.3 times 10 to the negative second. Now, because this number is so small, I can't cancel this out. So you will see that my number is attained essentially by the quadratic. So 4.3 times 10 to the negative 2 is because I can't cancel that x out. Can't do it. So my pH, because this is my hydrogen ion concentration, and it's my hydronium ion concentration, I could take the negative log of that, and my pH is going to be 1.36, which again is a pretty small pH, but it makes good sense, because HSO4 with that Ka of 1.2 times 10 to the negative second means you're going to produce a lot of H plus hydronium ion, however you want to describe it. So again, salts are same calculations, just you recognizing what you have in front of you in order to determine what steps you need to take.